Hello and welcome to the tutorial. So today I'm going to be covering a faster implementation of the stack in the queue compared to last time. And I'm going to be doing this using the runtime tester to see the runtime efficiency, the IntelliJ debugger, and some other tools. I'm also going to be showing Iterator in more detail, and overall it's going to hopefully be a very helpful tutorial for you guys. In the next tutorial, I'll be showing you how to install the runtime tester library so that you can plot the runtime efficiency of your own code. But this time I'll just be using it, and you'll see the videos on how to install it as they come up. It's not been quite finalized yet. So now I'm going to go into my IntelliJ. I'm going to open the project for the tutorial. You can look at a previous tutorial for instructions on how to clone the repository and get it working on your computer. And the link for this repository is in the description. So I'm going to check out the master branch, which has no solutions on it. And I'm going to cast my screen to you guys. Alright. So in today's tutorial, we'll be improving our list of links and making it run faster. But first, before we make it run faster, we've got to show what is slow about our linked list. And to do that, I'm going to use the library for the tester. To do that, I'm going to go project structure, I'm going to go libraries, and I'm going to add the library.jar that I downloaded, which I've put on my desktop. Alright, and now I'm just going to change my main to, instead of all this, well, it's going to still run all this, actually. I'd like to have my efficiency tests in addition to my completeness tests. We wrote all of this in the Monday section, or actually the Monday section in a previous tutorial where we wrote a linked list, a generic linked list. So if you want to learn how to write a linked list, go back to that old tutorial. This time I'm going to be showing you guys how to improve the linked list. So here, to start my runtime efficiency checker, I'm going to say visualizer.launch, and it's list of links tester.class. And I want to see which methods are running slow. So I'm going to test my stack and my queue. First, I'm going to add a benchmark to see, well, oh, I haven't written my stack and queue yet. That's right. Well, it's okay. We're going to write our stack and our queue. Then we're going to see how fast they run. And then we're going to see like if we can improve anything about our list of links. And for now, I'm just going to do the stack. I'm not going to do the queue. Because the queue is better to implement with a different linked list. We'll modify it first before we do the queue. But for now, we can do the stack. All right. And I'm going to say extends list of links. E, and I'm going to say stack E. And that's just because they're generic types. So now I just need two methods. I need a pop and a push. So I'm going to say public E pop, which takes no inputs. And it says E data is equal to get last. Because with a stack, you add the last element with a push. You put the last element on the top. And with a pop, it takes the last element off. So imagine a stack as a literal stack of objects. Here, I have got a stack of phones. And if I pop from my stack, it comes off from the top. If I push to my stack, it gets added to the top. Simple as that. That's a stack. It's a literal stack of stuff. So I'm going to get the last one. Then I'm going to remove the last one. And then I'm going to say return data. And the reason I save the data as a variable is that I want to get it before I return it. Or before I delete it. All right, simple as that. Then I need the other method, which is push. So I'm just going to say public e push e data. I'm just going to say add data, and that should add it to the end of our list. And it's not an E, it just returns nothing, so public void. Excuse the mistake there. So now we have pop and push as our methods in our stack. And in here, we can test those methods and see how fast they run. So we can test it for functionality as well, if we want to. We can see that it is, in fact, first in, first out. And you know what? Maybe we should do that as well. Here we've got a test stack methods function, which I'll call in main. And we can fill it in. So under test stack methods, I'm going to call that. And I'm going to fill in test stack methods by writing, let's say, integer test is equal to new integer. I'm just making an array of these things so I can add them to the list and see if they push and they pop properly. I'm just going to say 1, 2, 3, 4, 5. Right? Now I'm going to say for integer I in test. I'm going to create my, my stack as well. Don't want to forget to create the data structure. I'm going to say stack s is equal to new stack. Or I guess it's a, which stack is it? I'm just going to make sure it's not the Java stack, it's my own stack. Yep, that's my own stack, and I'm going to make it a stack of integers. So when it's generic, you just put these brackets. I'm going to say it's a stack of integer. S is a new stack of integers. And the generic thing is not needed on both sides. It's only needed on the left, but I'm going to put it on the right as well, just for the sake of completeness. Now I'm going to say s.push I. Right, and now I'm going to say for int I equals 0, I is less than s.size I plus plus s dot or system dot out dot println s dot pop. Right, and now here I can just say system dot out dot println I. Now, if you notice something, when I'm popping, my for loop is a lot messier than when I'm pushing, and that's just something to keep in mind. Like, look at the beauty of that enhanced for loop. It's just for variable type, variable name, colon, data structure, and it lets you access it without having this int I, all this manipulation stuff. That's not always necessary. It's a much simpler kind of for loop. And we want to think about it. Maybe we want that kind of for loop for our own data structure. That's something we might see later on in this tutorial with the iterator. This is what the iterator is for. So this for loop uses the iterator in the iterable array test. And you'll understand what all those mean soon when we improve our data structure. So now if we run this, we get 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, and it does our runtime testing, 5, 4, 3, 2. Oh, and then it, I think it cuts off before it actually finishes. So we go 5, 4, 3, 2, 1, 5, 4, 3, and then it stops popping. Why is s? Oh, that's because it does it until s.size. I'm silly. I should do test.length. So that's a mistake on my part. Let's fix my mistake and try it again. So yeah, now it goes 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So you can see that it indeed does work as a stack properly. But let's see just how fast our stack runs. So if I say add benchmark, now that's how we add a method to our tester. And we have to import that. Add benchmark, we'll say name equals our stack push. And we'll say public static long, because it has to return a long, push test equals, not equals, long input. And here I'm going to say, I'm going to fill the stack the same way as we did before, but instead of filling it from an array, I'm going to do something else. I'm going to create the stack data structure, and then I'm going to say, instead of filling it from test, I'm going to create a randomizer. So random rand equals new random. And I'm going to say, fill it in with the random integer from rand. So that's going to be for int I equals 0, I is less than input, which is the size, I plus plus, and the size is bounded by what's passed to us by the tester, s.push I, which is going to add it to our stack. And now here, now here we can just say long start time equal to system.nanotime. We're going to say s.push next int, and here should be putting and next int as well. And just to improve this, to have better practice, I can say int added equals rand.nextInt. So the only thing we're testing the time of is our push method. So I'm going to say added, and then I'm going to say long end time is equal to system.nanotime as well. And I'm going to say return end time minus start time. Now this might seem daunting because you don't know what these things are, so I'll explain it for you. So we're writing a method here which tests how fast our push works. First, we're filling the data structure with all of the different stuff we have to put in it. So we make a stack and fill it to the size which is input. Hopefully that makes sense. And there are video tutorials on how to use this library that I've published as well. So we fill the stack to the size of the input, and then we test its speed like this. I'm going to go into detail on this next tutorial, so don't worry about how it's done. We're just going to look at the results for now. So we're going to run it. Now our stack's push. This should be running at O of 1, remember. O of 1 means that it should be going about as fast as this O of 1 demo, or at least it should not be increasing as we add more stuff. So we're going up to 15 things. It's not really steadily increasing. If we add like 5,000 things each time, it looks like it's getting slower. This is not O of 1, and it should be O of 1, so we know there's a problem. Let's try our pop, just to see if the issue is isolated to push, or if you have a problem with pop as well. Pop is going to be really similar. We're just going to say pop test, and we're going to call it our stacks. Pop, everything about the method is going to stay the same, except here, instead of s.push, we're just going to say s.pop. I'm going to see how long it takes to pop. So I only just changed 2 lines there. I went from s.push inside of this statement to s.pop. That's all I did. It's the only thing I changed. I changed the method name, and I changed it from push to pop. Now I'm going to run it, and I'm going to graph our pop and our push. Now if we graph our pop versus our push, and we add in a ton of stuff, we can see our push was bad, but our pop is even worse. It's just awful. I can't stand to look at that. Garbage. Don't want it. So instead, what I'm going to do is I'm going to create a better linked list as the backend for our stack. The first problem with our linked list comes from what we're using to do the, let's look, because our pop was worse than our push, right? So what does our pop have to do? It has to get last, which is the same, or it's not the same, but get last. What does get last do? Let's go to it. Go to declaration. Well, get last returns get from size -1. Let's go to this. Okay, so we're actually going through and iterating through our entire linked list to get at our data, and that's just c'est pas bien indeed. It's like, it's not a good way to go about it, because we have to iterate through our data structure to get to it. When we could make an improved linked list, let's say for example one which has both a head and a tail. We could do a singly linked list with a head or a tail, but because I just want to go the extra mile today, I want to really flex on you guys, I'm going to be doing a doubly linked list to improve our performance. The reason for that? Well, this takes a long time. If I put breakpoints on this, IntelliJ style, that's just by clicking on the side of the line, and I run it, we're going to see how many iterations it takes to get to pop something of a big size. So right now, the stack has 1, 2, 3, 4, 5 in it, right? And the index is 4 because we're popping from it. So we're getting the last thing in the stack. It's going to go through, it's going to loop, it's going to loop again, it's going to loop again, and it's going to loop again for the number of things that's in our stack. That's where O of n comes from. If n is the number of things in our stack, and we have to loop through it n times to get to it, that is the O of n. That is what O of n means. It means that when we pop from it, the debugger is going to go like this. It's going to go loop and loop and loop and loop n times. We want to minimize that. We want to avoid loops. So the way we can avoid loops to make this work in O of 1 is, it's to create a doubly linked list, or at least a singly linked list which tracks its tail. So we can go, instead of having to do this like that, we can instead see what get first does. Get first just returns head. Easy peasy, get first is O of 1, because all it has to do is return the head. It's already saved. So we could keep track of a tail, and that would also work very fast. Or we could do the cooler thing and have a doubly linked list. So let's do doubly linked. First thing to change this into a doubly linked list is going to be to edit our list node. We don't just want a next, we also want a previous. And we're going to make these both private, because I like encapsulation. But we're going to have getters and setters for both of them. So this.data is data, and now we're going to get next, set next, and we're going to just create those same things, just generate a getter and setter for these ones. And just to follow convention, I'm going to, instead of saying set, no, I don't need the next ones either. So this set next, we don't need get next, we just want previous and set previous. All right. So now we can change our methods. I'm just going to kind of zero out the methods that we're not going to be able to use anymore. So first, we'll still return head. Get first is still fine. Is empty, still fine, except we also want to keep track of our tail now. So we can say private list node e tail. Right, now when we create our list of links, we have to also say tail is null. Okay, those are simple changes, right? Because I'm just adding a head and a tail to the list. That's a node at the start and a node at the end. Now when it's doubly linked, that means it's got a pointer to next and previous. So things like adding are going to be a teensy bit hard. But we can still do it, hopefully, with relative ease. So get first will return the head. That's fine. Size will return the size. That's also just fine. But get we don't want anymore with the index, because that's going to be, well, we can still traverse through. Actually, we can keep it, but it's slow. This is what causes the slowness of our algorithm. So we can keep it, but we're not going to use it. Same with get node. And the traversal like that still works, except instead of temp equals null, while temp does not equal tail. That's just so it traverses in one direction. We can also optimize the traversal, and to optimize the traversal, what we have to do is we have to make it say if it starts on, if the data is closer to the end of the stack, you start at the end and you go from the tail, and if it's closer to the start, you go from the head. But I'll leave that implementation for you guys to sort out. Here we're going to deal with adding. So our add method before worked with a singly linked list, and that's fine. But we're doubly linked now. So we still have to create a new node, and we still have to say this.head equals new node, this.tail now has to equal null. And then, okay, that's fine. And if it's blank, we have to say this.head.next equals tail. And here actually we could say new list node. This is going to be a dummy node. It's going to have null in it. Right? So we're going to say this.head.next is going to be the tail. This tail is that. This.tail.previous equals head. Now that's kind of doubly linked our list when it's just created for the start. So that's the base case. That's when we just have it. So the head is going to be our new node. Or we can do this alternatively. If we don't want to use a dummy tail, because we're still thinking about how we're going to create this, right? So a dummy tail could work. Or what we could do is we could just say this.tail is equal to head. Equals head. So this way, what happens is that, well, our head and our tail are going to be the same node because it's of size 1, right? So then we have another case here. This is no longer good enough to do our non-base case. And now we can say if this.head, oh, we forgot to say this.tail.previous equals head. Well, we don't need to yet because it's not linked yet. So, right, so now we can say, now if this.size is 1, we can kind of relink our list better. So we can say this.head, or no, first we have to create a list node. So we can say, oh, we already did? Okay, so we can say this.head.next equals new node. So we're linking that up. Then we can say new node dot previous equals head. And we can say tail equals new node. And that's kind of linked up our list to add at size 1. So now we can do else if this.size, well, actually we don't need to do an else if, we can just do an else. Now else we can say, and we also need to do size plus plus, let's not forget about that, except size plus plus is handled over there. So we can just do it like this. So just one size plus plus, keeping track of the size properly is very important. So now else we're going to say this dot tail, or we'll say list node this dot tail dot next is equal to new node. We're going to say new node dot previous equals this dot tail, and we're going to say this dot tail equals new node. And that's what it's doing, is it's basically linking up our node to be the new tail. And this is going to add it to the end of the list. So let's just remember here that add to the end of the list. Right? That's going to add it to the end of the list. Now let's make sure this still works properly. So we're going to go into here, and we are going to run it with the debugger, and just to see that it's behaving exactly like we expect, because it's important to see if it's doing what we want. So it's going to start off with data being 1, this having nothing in it, and having a size of 0. So we go into here, head is null, head is the new node, head is tail, size is 1. All right, now the data is 2, the size is going to be 1. We go through, we're going into the second base case. We say our head is now the new node, or our head of next of head is the new node. New node's previous is head, tail is the new node. So if we look at our linked list, our tail, the previous goes to the head, the next of the head goes to the tail. Now it's doubly linked. Now we go forward again, and we're in neither base case now. So we can say this.tail.next is the next node. So now we can watch our tail here. Let's watch our tail. So right now, next is null. We add it. Next is no longer null. Okay. and our tail is 803, and the next is 818. That's just the memory address, right? So we keep track of the references. So the previous of the new node is now this dot tail. So if we look at the new node, which is 818, which is right here, right now we have no next and no previous. Then we have a previous set. So now it's behaving like a tail, where next is null and previous is set to blank. And now tail is no longer acting like a tail because it has a next. So we go to the next one, and this one becomes the tail. That one is now no longer the tail, and we go through, and now it's just going to do that case forever from now on. So we can be pretty sure that our algorithm is good. Now, if we just want to see that our stack push and pop work, well, wait a minute. Is it good? It might not be. Let's see. This just returned null for, that was the first pop of the day. So why would the first pop of the day return null? Let's see. eData equals get last. Let's see what get last does. Get of size -1. Oh, I see why. Because I changed our get method and I screwed it up. But I screwed up our get method and it doesn't matter because we're no longer using, remember I said we don't want to use get ever again because it's O of n, it's slow. So instead of that, why don't I just, right, that method was broken, but why would I even keep that slow method? I'm going to fix it, I'm going to do it better. So now if we scroll up to the top, 1, 2, 3, 4, 5, 5, 4, 5, 5, 5, 5, 5, 5, 5. Why is get last not working now? It's tail, and now what else do we have to do? We have to remove last. Okay, so we didn't actually change our remove last method, so let's do that. Okay, so this doesn't work very well. Else get node dot set next null, because remember we also have a previous, so it doesn't work anymore like we expect, because that last just returns tail. This just sets the next to be null, but we're traversing the list from the other direction now. So if we want to remove the last thing, we can say tail dot previous dot next equals null, right? Because we're setting the reference of the thing before the tail to be null. Now the tail links back to that, but that link just deletes the link to the tail, and now we can say tail dot previous equals tail, or actually it's tail equals tail dot previous. And now that should successfully remove the last thing from our linked list. If we want to verify that works, let's see if our 54321 works as a 54321. And it does. Look at that. Now, let's see if making these small changes has improved our runtime efficiency at all. We're going to run it. We're going to see our stacks push and pop, and we're going to compare it to O of 1. Oh, and look at that. Yeah, pop is slower because it also has to remove. But I'm not noticing any slope upwards. Well, a little bit maybe. Let's just do a lot of stuff. I said a lot of stuff. Okay, so we got some spikes there. We got a little bit of spikes. But look at that. We are now at 20,000, 200,000. We're at 200,000 items in our stack. If we tried 200,000 items in our last method, this would be taking years to run on my computer. Years. But on this computer, which has not gotten any faster, I've just gotten 500,000. It's going to get to 1 million eventually. It's just going at O of 1. And that's the beauty of O of 1, and that's the beauty of optimization. But we're not done because we still have methods that don't work in our linked list, and we want to get a fully working doubly linked list, and we still don't have a queue. So let's deal with those things. And the reason that there's this spike in the O of 1 is I was changing my constant factor to be more realistic. So in this simulator, we have a step time, which is how long each step takes. Because remember, the big O notation just tells you how it increases. But the speed of each step isn't actually a factor. Anyways, nonsense for another day. Important part is, we've gotten our methods to run in O of 1. That's a speed optimization of an absurd factor. Great job, me. Great job, you. Great job, everyone. Perfect. We love it. Now let's deal with the rest of the methods. And then afterwards we can get to our iterator, which we will do in linked list. So, add. Okay, add works. We like add. I'm going to take the debugger points off. What do we need? Well, we need a get first and a remove first, right, to be able to do a queue, because a queue is last in, first out. No, a queue is first in, first out, what I'm saying. Stack is last in, first out. Alright, so get node, we don't need this anymore, we don't use it. Get, we will actually be using. So I'll keep get. And this one needs to be temp is not null. So we're going to remove get node. We don't want to use it. Well, actually, you know what? Get node works. Get node works, so we're going to keep it. But it's slow and it's bad. But you know, I really don't like it, so let's fix it. Remember, we can traverse the list either direction now. So what we can do is we can actually say that if we're closer to the end, we can traverse from the start. And I'm going to keep get just so we have a comparison point. I'm going to get a get, and I'm going to create a get faster. I say get faster. Right? Now get faster is going to say if this dot size is just size. If size is going to be greater, no, if index is going to be greater than size over 2, we're going to start from the end. So here, start from end because closer to end. And here we're going to say else, which is start from size, from start because start is closer to index. And we'll keep our default stuff here. We'll just keep this one as the thing that goes into both the if and the else. But the rest of it's unique between the two, kind of. So, and this method is for we're going start to end. Now let's adapt this to be end to start. So now end to start, we'll start the counter at size instead. All right, size or size minus 1, I suppose. And now we're going to say edata is null while temp is not. And now this is going to start at the tail. It's going to counter minus minus. And let's try it out. So all I did was I reversed the direction. Everywhere where it said head, I said tail. And I forgot to say previous here. So everywhere where I said head, I now said tail. Everywhere I said next, I said previous. Everywhere where I said plus, I said minus. And where I said 0, I'm saying the maximum index. So let's try it. Oh, we don't have anything to test it with. Silly me. Okay, let's make some tests. First, let's verify that this works. And you know what? Before we test it, before we verify it works, let's implement it for something useful. We're doing the iterator now. So the iterator is what lets us use a fancy for loop, an enhanced for loop. So if we look at them, right, where do I use it? I use an enhanced for loop somewhere here. Here it is, enhanced for loop. This kind of for loop uses an iterator. That's what the iterator does. What it's doing? Well, I'll explain it when I implement it. So first thing, I need to implement iterable. Iterable is an interface. An interface is like a class, except not really. Imagine it like a protocol. I went over these earlier on in the Mafia episodes, like episode 3, episode 2. An interface is, imagine it like in Swift with Apple's programming language, they call it a protocol. It's a series of methods by which you know that things are standard in the way they communicate. So I'm going to implement iterable. I'm going to implement the methods. For that, I need to implement a method called iterator, which returns an iterator. So what the heck is an iterator? Well, an iterator is another interface. So you can use an interface in the same way you use an abstract class, which we've shown off in previous tutorials. If you're rusty on that, you can go back and watch the previous one. So an iterator can be used like an abstract class, kind of, where you can instantiate something as an interface. So you have to create an internal class which implements this iterator interface to be able to return one, because we have to make an iterator for our data structure. So I'm going to say, class list of links iterator implements iterator, and it's going to do of type E. Now I'm going to open it up, and I'm going to have it read again. An interface specifies a list of methods, but not how to do them. So I have to implement those methods, and I have to do them myself. So the method is has next and next. Now we can imagine how the iterator in the enhanced for loop works. All that the enhanced for loop is doing here, where it does for this, is it's doing while has next, get the next. So really, all that is it's secretly saying while s.iterator dot has next. Well, actually, what it's doing is it's saying iterator, and you'll never have to do this. Remember, I'm just showing you what the for loop is doing. You'll never have to write this code. Iterator, integer, iter is equal to s dot iterator. And now it's going to say while iter dot has next, integer I is equal to iter dot next. And it's going to say s, oh, and I'm going to copy paste what's inside this one. So these two are equivalent things right here. So this is the same as this. It does the same thing. Now if we run our tester again with our test stack methods, while iter has next, null pointer exception, what's wrong with that? While iter dot has next, s dot iterator. Oh, our stack has no iterator. That's why I meant to say test. Oh, it's actually going to be a different one. It's going to be array. Array dot. You know what? Screw it. I don't know how to do it for an array. I don't remember. Instead, I'm going to do it with an array list. So if you'll excuse me, array list integer iterator tester is equal to new array list. And I'm going to say arrays as list test. You realize I could have just used arrays as list test anyway. Anyways, doesn't matter. Iterator equals iterator test dot iterator. Okay, excuse me there. I made a mistake with the array. I know there is a way to get an iterator out of an array. And that's what the for loop is doing. But I don't know that way off the top of my head. So instead, I'm just going to use a abstract data type like this one. And then I'm going to say, while iter has next, iter.next, system push I. And now here, just to make it consistent, I'll do iterator test as well. And now I'm going to show you that these two pieces of code are equivalent. So we're going to run it. We're going to not do that. And we're going to say 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. And then it does the same thing twice, basically, with this part and with this part. And I'm not sure if that code is exactly the same as with an enhanced for loop. I might have made a mistake in it as well, but that's kind of the point of it, at least. So now I'm going to be able to go back into list of links, and we can implement our iterator. So to do an iterator, we have to keep track of what the index of what we're doing is. So we can say int counter equals 0. And now has next, we're going to say return counter is less than size of our data structure, right? Here we're not going to throw this exception because I don't care. Next, we'll just return get, and I'm going to say counter. And then we have to iterate counter, so I'm going to say counter plus plus. And now, what's wrong with that? Oh, I put it after the return. I'll just put those in the correct order. Return get counter. All right, now let's see if it works. If I iterate through now my list of links, I'm going to say for I. Now I'm going to see how fast this iterator works. Oh, no pointer exception. Yeah! All right, let's peep this out with the debugger. All right. What's poppin' here, fellas? Return counter. I'd rather have size than counter. Oops. No, that's fine. List of links iterator. Oh, that's why. So we have to not forget to return our iterator. Remember, we are not returning null here. We have to return the class we just made. An alternative version of this is you can declare it as an anonymous class, which is something to do with interfaces. I'll show you that right now, but don't get confused by it. If you feel like what I'm going to tell you right now is going to confuse you, pretend I didn't tell you. Skip forward a bit, or like just mute yourself for this time. If you feel like this is going to confuse you, it's really simple, but it's not related. It's just a little detail that I'm showing you about interfaces that might come in handy. So I'm going to say return new iterator. And now you can see it's asking me to fill in the interface again. This is what's known as an anonymous class. Don't want this part. I just want none of the class definitions, just like that. So this is doing the same thing, except instead of defining my class in an internal class, I define my class anonymously. You won't really have to do this in Comp 250 to my knowledge, but it's another way to do an iterator. So I'll do it like this for now, just for the flex. And index 5 out of bounds for section 5, because remember, we can't go all the way up to size. We do have to go size minus 1. And now, we should have a solid iterator. And we'll just minimize that for now. So 1, 2, 3, 4, 5. 5, 2, 3, 4, 5. No, it's 2, 3, 4, 5. Right, so we missed the 1. So we put our counter plus plus before our return counter. That's another common mistake. This looks like it's shorter. It's not actually as good, so we can now instead say e cur is equal to get counter, and my variable names are arbitrary, of course. And counter plus plus, and then return cur. So this way we're not going to miss our first index, and we don't have to do size minus 1. Similar simple correction, and now we have a good iterator. Hopefully. Now we go, let's see if it goes 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Because remember, this one doesn't just pop, so it goes in the same order. And perfect. Now we have implemented iterator for this. Now, let's see if our improved get method still works, or if it works at all. Let's see if our get faster method is doing the same thing. Oh, that felt fast. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. So our get faster method works. But now, let's see if it's actually faster. So we remember how to do a benchmark in this library. We're just going to say at benchmark. And benchmark name equals our get. And now we're going to say, let's make it get from the end, because the end is going to have the biggest difference. It's going to be the same from the middle, and it's going to be better as it approaches the end. So it's going to be the same all the way up to the middle, and then better and better and better as you approach the end compared to get slower. And you can do multiple tests to prove that if you want to. I'm just going to show you a demonstration of it being faster for today. So now we're going to say s.get, and then the index will be the last one, so input minus 1, or just input, why not? Provided long, I'm just going to cast it to an int. I know that's not technically super proper, but it's okay. And instead of pop test, I'm going to call it get test. And now I'm going to do the exact same one, except I'm going to make it use the get faster method. So I'm going to say get faster. And I'm going to say s.getFaster input. And now let's race them. And we don't want any of these math demos. We just want our getters. Oh, and there was an error. What is it? A lot of errors. Hold on. Let's peep this out. Long input. Index 1 out of bounds for size 1. Well, now we've got a problem with that. Index is not size. Did we not properly fill our array? Oh no, it's because I forgot to put -1. I thought it would be okay because I thought we were pushing right before, but we were not. Because the reason I made this mistake was that in our previous thing I copy-pasted, I put an s.push before, so it would be of size input. But here I do it less like that. I could do greater than or equal to input. It's a matter of semantics. It's just because the reason I made that mistake was because here I was pushing to the stack and I forgot I removed that line. It's good I removed that line. I was supposed to. Just didn't make that connection in my mind. So the mistake that caused all these exceptions was that I did not get from the right index. Now if I get from an index that exists, I should be able to plot these things for us really nice. Our get and our get faster. Now our get faster should be roughly 2 times faster than our get. Isn't that beautiful? It's almost exactly 2 times faster. Let's crank the data. Let's crank how intense the test is. Oof. Oh, actually, our get faster looks like it's O of 1. That's not right. Something is wrong about our get faster. But we verified it works the same. So why is get faster so much faster? Wait a minute, it's not. Because we're getting from the last index, right? So actually, it should be O of 1. That's the genius of it. It's that much faster, not only because it's faster at getting towards things that are close to the end. If we're getting the end, it's like way faster. Let's try one that's to show off that it's not actually just twice as fast. It's going to be over 3. So we're going to say input over 3. Input over 3 should be roughly twice as fast. So yeah, this one can be infinitely times as fast, twice as fast. It's a hard comparison to make. So twice as fast might not have been a complete truth here. It's actually a lot faster with this optimization. Let's try it. So now we're getting from size over 3. Our get faster is taking consistently less time, and as we crank our data set, our get faster should be consistently just a bit faster than our get slower. These spikes are not actually really to do with our algorithm necessarily. It's more to do with my computer having some slowdowns due to the GUI and stuff. So they're kind of at parity when we're getting from close to the middle. This is at 1/3, but faster should overall on average be a little bit faster, because instead of going from, oh, no, never mind, I'm talking nonsense. It was only faster by a fluke. What I meant to say is input 2 times input over 3. Now that I've corrected my terrible blunder, now it will actually be faster. I was talking about the theory there. I wasn't really reading it, but yeah, sorry. It's supposed to be input 2 times input over 3, right? Because we're past the halfway point. As long as we're past the halfway point, our get will be faster by a lot. So like the speed improvement gets better as you get closer to the end. So now if we're near the 2/3 of our get faster, the speed improvement should be quite substantial with our get faster. Let's see. Yeah, our get faster is a lot faster, and as we increase our steps per iteration, you see it's no longer O of 1. It's only O of 1 at the start and the end. But it's consistently much faster than our get. Way faster. So way better algorithm. Hopefully that makes sense to you guys. So now in extreme speed, I'm going to implement the queue. You've never seen a queue implemented this fast. What do we need for a queue? Well, the prescription calls for a couple things. First things it calls for is a get first. We already have it. And remove first. Do we already have that? No, we don't. So let's get a remove first. Right. Or it's going to be, yeah, public void remove first. So we're going to say if this dot size is less than 1, less than or equal to 1. This dot, well, head is null. Tail is null. Right, now else, we're going to say this dot head is equal to this dot head dot next. And I'm just saying this dot and not this dot interchangeably at this point. This dot head dot next. And we want this dot head dot previous equals null. Right, and now there's another case here though. There's the case of the size. If the size is 1, if the size is 2, what are we doing? We're doing that. No, actually, it works fine because our tail will not really be changed, I don't think, ever, unless we get to the size 0, because here our head just becomes our tail. We can confirm that though, and we will confirm that in our queue. So we're just going to create a new class called queue. Now you might be wondering, why does the iterator still work in stack and queue? It's because these extend list of links, and list of links has that method, so this one has the method available too, and the traversal is the same because it's based on it. Extends. Right. Now here we can add public void enqueue, which will say add first. Do we have an add first? No, we don't. So we have to create our new method. Oh, we don't have to add first, right? Because that's for our... yeah, we just have to remove the first. We have to get our first. But we don't have to ever remove our first. Or wait, no, we don't have to ever add our first because we're adding to the top, removing from the bottom. So actually, we're good. We're going to say in queue, and it's going to say add data. Very simple. And dequeue, edata, or not edata, it's just going to say public edequeue. Sorry, I'm getting my method declarations a little bit jumbled in my head right now. We're going to say edata is very similar to pop. Edata is equal to get first. And then we're going to say remove first. And then we're going to say return data. And why is it red? It's probably because get first returns a node rather than a... yeah, it returns a node. We don't care. We want E, so we want a head.data. All right, now this should indeed work. Now we're just going to test our queue the same way we tested our stack. So we're going to copy paste our entire test. And where is stack test here? No, we don't have one, or we'll make one. We'll just copy paste this method. And this is just so we can verify our queue works. So test test queue methods. Now instead we're just going to create a queue. Is a new queue. Right, now for integer and test dot in queue. Now we're going to do the loop, and then we're going to say dequeue. Now let's see if our test queue methods work. We're going to do our Alright, and now I'll get rid of my test stack methods just so we don't get things jumbled up. And we're going to look at our null pointer exception under remove first. So 5, 1, 2, 3, 4. And now our 5 is giving us a null pointer exception. Why is that? Right here. Oh, if this dot size is, it would rather eat 1. Oh, I forgot to do size minus minus. Silly Billy. That should hopefully fix our problem. So we go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's how a queue works. First we add 1, we add 2, we add 3, we add 4, we add 5. We do our for loop, we go 1, 2, 3, 4, 5, we do our dequeue. It works. And we can we know that because our stack and our queue are so similar that they're probably going to run in the same time efficiency. We don't really have more time for today, so that's going to be, I'll ask you to take my word for it or to test it yourself. But that's our stack, that's our queue, and that's how it all works. That's our iterator, and that's runtime efficiency explained. Hope you guys had a fantastic time. I'll see you next week when I am when I'm explaining to you how to use the runtime efficiency tester to test your own code. There's going to be a lot of videos on that, and that's going to be your debugger kind of for assignment 2. So I hope you guys had a fantastic day today, and I'll see you later. Thank you.